There is a persistent idea driving billions of dollars in clean energy policy, the concept of water as a fuel. In reality, water is the exact opposite. It is spent fuel. When hydrogen oxidizes and releases its energy, water is the exhausted, low-energy byproduct left behind. You cannot extract surplus energy from a state that has already descended to its baseline. This diagram illustrates closure theory. Left, water rests in deep, stable closure. Center, water splitting requires closure charging, supplying irreducible external energy to lift the system from its baseline. Right, the isolated molecules are separated closure potential, holding the specific energy you just invested. To find the actual commercial limits of the hydrogen economy, we have to map the immutable physical floor of this reaction, engineer our way past its primary architectural bottleneck, and establish a strict hierarchy for where hydrogen makes economic sense. Treating water as a primary fuel leads to heavily flawed economic models. Acknowledging it as spend fuel correctly reorient hydrogen as an energy-intensive storage vector, one that requires massive external power to create. Before attempting to scale up commercial electrolyzers, we first have to quantify the baseline energy required to split the water molecule under perfect conditions. This chart maps the thermodynamic floor. The blue line at 1.23 volts represents the absolute minimum Gibbs free energy required to force water into separated potential. The white line at 1.48 volts accounts for the thermoneutral enthalpy requirement, including necessary heat exchange. Real-world commercial electrolyzers never operate at these theoretical minimums. They require significantly higher operating voltages just to produce hydrogen at a usable rate. This graph maps the resulting overpotential. The amber zone arching over the theoretical curve represents excess kinetic waste. Looking at the lower diagnostic modules, we see this is caused by sluggish intermediate chemical formations and physical gas bubbles blocking the electrode surface. The goal of electrochemistry is not to hunt for free energy from water. The goal is strictly to shrink this amber zone of overpotential, compressing the reaction as close to the 1.23 volt physical floor as possible. To shrink that amber zone, we have to isolate exactly where the kinetic waste is being generated inside the electrochemical cell. This schematic compares the reaction's two halves. The top hydrogen evolution reaction is a straightforward two-step process. The bottom oxygen evolution reaction is a dense four-step sequence. Step 3 is the critical bottleneck, where forcing oxygen bonds to form drags down system efficiency. This is where catalysts enter the equation. They do not create energy. They act as closure pathway modifiers, engineered to stabilize these difficult intermediate oxygen states. This chart illustrates kinetic resonance matching. The peak represents an ideal catalyst perfectly aligning its binding energy with the reaction. The arrows show failure states. Binding too weakly fails to activate, while binding too strongly leaves the surface permanently trapped and useless. A breakthrough catalyst works by providing a high-fidelity, resonance-matched pathway. It executes the oxygen evolution reaction with minimal energy loss, staying as close to the thermodynamic minimum as physics permits. Discovering a highly active catalyst in a controlled laboratory environment solves only a fraction of the problem. Without an industrial architecture to protect it, that catalyst will rapidly degrade under real-world stress. This exploded schematic shows the integrated architecture. Component 1 is the catalyst gate. Component 2 is the support scaffold, maintaining structural shape. Component 3 is the membrane boundary, selectively allowing ion transport while strictly enforcing the separation of the resulting gases. This diagram outlines severe boundary failure. If the membrane develops a pinhole, hydrogen and oxygen cross over, creating an explosive hazard. The bottom panel illustrates identity loss, showing how extreme voltage, heat, and shifting pH actively dissolve the catalyst over time. Building a viable hydrogen production system is an exercise in balancing tension. The architecture must permit extreme catalytic activity while enforcing long-term durability and safety. That careful balance is immediately threatened when we move away from pristine laboratory water and attempt electrolysis in impure environments, like seawater or industrial runoff. This graphic depicts a crowded reaction field. Trace contaminants, magnesium, and chloride ions swarm the electrode. They physically block the catalyst surface, and trigger competing chemical reactions that cannibalize the system's efficiency. To solve both the issue of water purity and the massive energy drain of the oxygen bottleneck, chemical engineers developed a structural workaround known as hybrid electrolysis. This chart compares pure with hybrid electrolysis. Instead of oxidizing pure water at high voltage, the hybrid system replaces water with alternative organics at a significantly lower voltage. Feeding urea or biomass into the anode generates clean hydrogen while simultaneously breaking down industrial waste. Rather than brute forcing the massive thermodynamic drag of oxygen evolution, hybrid electrolysis intelligently couples hydrogen production to the chemical breakdown of waste, lowering energy demand. Producing separated hydrogen potential is only half the equation. The other half is applying strict economic logic to deploy it without wasting grid capacity. Because of the energy penalty from closure charging, hydrogen cannot be a universal replacement for fossil fuels. It is a specialized carrier of exergy. This diagram categorizes the three specific systemic constraints that hydrogen is uniquely engineered to solve. It transports energy across spatial displacement, it provides long-duration storage across time, and it acts as a chemical reducing agent for industrial matter. To prevent massive efficiency losses, grid planners and engineers must adhere to a rigid direct electrification hierarchy. This chart establishes the hierarchy. Tier 1 uses electrons directly for motors and heating. Tier 2 assigns short-duration storage to batteries. Tier 3's rule sets hydrogen's threshold. It is rational only when energy must wait across seasons, cross oceans, or embed into heavy manufacturing. This diagram maps the unbroken logical chain. We lower the gate through resonant catalysis, we preserve the potential through durable membrane architectures, and we deploy the charge strictly where electrons cannot go. A mathematically sound energy transition requires accepting these limits. The physical floor is thermodynamic, the engineering breakthrough is kinetic resonance matching, and the ultimate role of hydrogen is strict exergy logistics.